It started in 2018, a sudden piercing blue flash in the deep sky. It was an explosion so intense it made the average supernova look like a flickering candle. But the physics didn't add up. Supernovae are slow-burning forest fires. This was a violent short circuit. It appeared out of nowhere, peaked with the energy of 100 billion suns, and vanished in mere days. We call them ELF-bots, a polite scientific label for "we don't know." But in 2023, a new event shattered that uncertainty. If it wasn't a supernova and it wasn't a mistake, then the anomaly pointed toward a far rarer engine, possibly a kilonova one that our models were never built to handle. For a brief moment, we thought we understood how neutron stars died until a kilonova refused to behave. The historic detection of GW 170817 in 2017 gave us a neat, tidy picture. Two stars collide, ripple space-time, and fade away in a predictable red glow. It was a textbook case, but the universe has a habit of punishing arrogance. As we upgraded our eyes specifically through wide-field surveys like the Zwicky Transient Facility, ZTF, that textbook began to fall apart. Unlike older telescopes that stared at deep fields for weeks, ZTF scans the entire northern sky every 2 days. It was built to catch the fleeting ghosts of the cosmos, and it worked too well. It started flagging events that defied the standard decay rates of radioactive elements. These events were labeled luminous fast blue optical transients, a bureaucratic name for a chaotic reality. We are here to conduct a scientific audit on these files. We are not just looking at pretty lights, we are looking at data signatures that violate 3 fundamental constraints of astrophysics. First, the energy budget. How can an object be this bright without an obvious source of mass or fuel? Second, the location constraint. How can a star die where no star has ever lived? And third, the geometry violation. How does an explosion become a perfect sphere against the laws of rotation? The models are failing. The simulations are crashing. We are looking at a system error in our understanding of stellar death. But speed was only the surface. The real anomaly lay in the energy behind it. If this is an explosion, why does it behave like a switch in the standard model of stellar death? Giant stars do not simply vanish. They die with a long, agonized groan. A typical Type Ia or Type Ib supernova acts like a forest fire. It ignites, spreads, and takes weeks or even months to reach its peak brightness as radioactive nickel-56 decays into cobalt and then iron. The light curve the graph tracking its brightness over time is a gentle slope, a mountain that takes time to climb. But on June 16, 2018, the Atlas HKO telescope in Hawaii captured something that violated this rhythm. It was a flash designated AT-2018 Cow, affectionately nicknamed the Cow by the random letter generator of the International Astronomical Union. But there was nothing gentle about it. The Cow did not climb the mountain. It teleported to the summit. It went from complete invisibility to peak luminosity in less than 3 days. And that peak was terrifying. It shone with the intensity of 10 to 100 times that of a normal supernova. If a standard supernova is a candle, the Cow was a floodlight aimed directly at Earth. Then just as quickly it began to dim. This behavior, rising fast, shining hard, fading instantly, is what we call a cosmic short circuit. It suggests that the energy source is not the slow burn of radioactive decay. It implies a different mechanism entirely. When astronomers looked closer, the data became even more contradictory. In optical light, the kind our eyes can see, the explosion was optically thick. That means photons were repeatedly scattered and reabsorbed before they could escape like a high-beam headlight trying to pierce a wall of lead. Yet in the X-ray spectrum, the Cow was screaming. It was luminous in high-energy radiation. This creates a physical paradox. How can you have a dense, foggy shroud that blocks visible light, but lets X-rays blast through? The strongest audit-grade explanation is that we aren't looking at a simple explosion. We are looking at an engine. Somewhere inside that debris field, a central object was actively driving the event. It was likely a newborn black hole or a hypermagnetized neutron star known as a magnetar pumping energy outward like a piston. The Cow wasn't just dying, it was powering up. This was the first crack in the facade. We realized that the universe had a way of releasing energy that bypassed the standard supernova budget. But identifying the anomaly was only the first step. Naming it would prove to be even harder. We gave it a name, LFBOT, short for luminous fast blue optical transient, hoping that would explain it. It didn't. In science, sometimes a label is a precise definition, but other times it is a blindfold we wear to feel safe. Following the discovery of the Cow Wide Field surveys, like the Zwicky Transient Facility known as ZTF began hunting specifically for these fast blue flashes. And they found them. In September 2018, they detected an event nicknamed the Koala, officially cataloged as ZTF-18AB Kilonovae. In 2020 came the Camel, known as ZTF-20A Sigmal. A cosmic zoo began to form. They all shared the same violent signature, a rapid rise in brightness, extreme blue heat, with photospheric temperatures reaching 30,000 Kelvin and a refusal to behave like standard supernovae. But here lies the epistemic trap. By grouping them together, we may have committed a classification label bias. Are all LFBOTs the same thing? Or is LFBOT merely a wastebasket taxon, a category where we throw everything that is too fast and too bright for our current models? Some of these events might be failed supernovae stars that collapse directly into black holes without a massive ejecta cloud. Others might be tidal disruption events, black holes shredding passing stars. And some, the most dangerous ones, might be the elusive kilonovae wearing a disguise. The spectrum of these objects was disturbingly clean. A normal supernova spectrum is messy, full of absorption lines telling us, here is hydrogen, here is helium. The Cow and its cousins were largely featureless blue continuums. They were hot, expanding fireballs that hid their chemical fingerprints. It was as if the event had erased its own spectral fingerprints. We were stuck. The physics suggested a central engine, but the data was too chaotic to confirm which type. Was it a black hole eating a star? A neutron star merging? Or something new entirely? We needed more leverage. We needed a clue that didn't depend on complex nuclear physics or messy spectrums. We needed something simpler: location. If we could pin down where they occurred, we could constrain what they could be. Supernovae live in spiral arms. Kilonovae can drift away. So when the next major LFBOT appeared in 2023, we rushed to pinpoint its address. And that's when the investigation took a dark turn. If the physics was confusing, the geography was about to become impossible. One of them detonated where stars aren't supposed to exist. The light didn't just break physics, it broke geography. To understand why AT2023FHN, codenamed the Finch, was so disturbing, you have to understand the real estate of the universe. Massive stars, the kind that create LFBOTs and core collapse supernovae, have a very specific lifestyle. They are born in dense gas-rich nurseries within the spiral arms of galaxies. They burn through their fuel, ravenously living only a few million years. In cosmic terms, this is a blink of an eye. Because they die so young, they never have time to travel far from home. Finding a massive star exploding far outside its galaxy is like finding a tropical orchid blooming in the middle of an ice sheet. It shouldn't be there. But on April 10, 2023, the Zwicky Transient Facility flagged a new blue flash. When astronomers pointed the Gemini South Telescope and the Chandra X-ray Observatory at the coordinates, they found the explosion pulsing 3 billion light-years away. But they didn't find a galaxy. The Finch was sitting in the dark. The nearest spiral galaxy was a staggering 15 kiloparsecs away, roughly 50,000 light-years. To put that in perspective, our entire solar system is only about 8 kiloparsecs from the center of the Milky Way. The Finch wasn't just in the suburbs, it was in the desolate wilderness between cities. This creates a severe location constraint. If the Finch was a standard LFBOT caused by a massive star collapsing, that star would have had to travel 50,000 light-years in its short lifetime. To do that, it would need to move at several thousand kilometers per second, a velocity far beyond what standard stellar dynamics allow. This anomaly forces a re-evaluation of the suspect list. Massive stars don't travel well, but neutron stars do. When a supernova explodes, the remnant core can receive a natal kick, a physics-driven punt that launches the neutron star into the void. If the Finch was the result of two ancient neutron stars merging a kilonova event, its location makes more sense. These stars could have been kicked out billions of years ago, spiraling around each other in the darkness for eons before finally colliding. It seemed like a closed case. The Finch was likely a runaway kilonova. But a good auditor doesn't trust the first alibi, because finding a kilonova that looks like an LF-bot blue hot and fast instead of a standard red transient creates a whole new mess of contradictions. And there was another possibility, one that questioned not the star, but our ability to see it. In science, nothing usually means nothing detectable. When we say the Finch exploded in the void, we are making a dangerous assumption based on the limits of our vision. We are assuming that because the Hubble Space Telescope didn't see a cluster of stars around. The Finch, no such cluster exists. This is the host non-detection problem. At a redshift of z equals 0.24, roughly 3 billion light-years away, a small and faint collection of stars such as a globular cluster would be incredibly difficult to resolve. Globular clusters are ancient balls of stars that often orbit far out in the halos of galaxies. They are exactly the kind of retirement homes where you find old neutron stars waiting to merge. So we are trapped in an epistemic bias. Scenario A. The Finch is a runaway, a system kicked out of its galaxy by violent physics. Scenario B. The Finch is a hidden local. It's sitting comfortably inside a star cluster that is simply too faint for our current instruments to render. If scenario B is true, then the Finch isn't breaking geography. It's just exposing the blindness of our telescopes. It challenges the homogeneity of the LF-bot class even further. Are we looking at a kilonova that just happened to look blue because we viewed it down the barrel of a jet? Or is it a new breed of explosion entirely? The Finch left us with a hung jury. The location ruled out standard massive stars, but the lack of a visible host prevented us from confirming it was a globular cluster event. We were left staring at an event in the desert, unsure whether it was truly isolated or simply hidden by the limits of our instruments. A dead star in a dead zone. Unless the zone isn't dead, we are just blind. But even if the address is uncertain, the shape of the explosion cannot lie. Geometry is harder to fake than location. And when we finally got a clear look at the shape of a confirmed kilonova, the data didn't just break a rule. It insulted a law of physics. Now we're not arguing about brightness, we're arguing about geometry. In astrophysical systems, angular momentum is usually an unforgiving constraint. The law is simple: when things collapse and spin, they flatten out. Spin a ball of pizza dough, it becomes a disk. Spin a collapsing gas cloud, it creates a solar system on a flat plane. Spin two neutron stars spiraling into each other at relativistic orbital speeds, and the resulting explosion should be flattened. For years, every major hydrodynamical simulation agreed a kilonova should look like a flattened pancake or a donut of debris flung out primarily along the orbital plane. The poles where the jets blast out might be clear, but the bulk of the matter, the gold, the platinum, the heavy stuff should reside in that thick, swirling disk. Then came the data from GW 170817. This was the historic 2017 event, the Rosetta Stone of kilonovae detected by both gravitational waves and telescopes. At first we were just happy to see it, but in 2023, a team led by Albert Sneppen at the Cosmic Dawn Center revisited the spectral data, specifically looking at the fingerprint of strontium. Strontium is a heavy element created in the blast. By analyzing its P Cygni profile, a specific shape in the spectrum caused by expanding gas-blocking light, the researchers could map the velocity of the debris. If the explosion were a disk, we would see different velocities depending on whether we were looking at the face or the edge of the disk. The Doppler shifts would be uneven, but the audit returned a shocking result. The velocities were consistent in every direction. The explosion wasn't a pancake, it was a ball. The analysis indicated the ejecta was highly spherical, almost symmetrical. This is a massive violation of expectations. In a system defined by extreme rotation where two stars are whipping around each other hundreds of times a second before impact, sphericity shouldn't happen. Rotational energy naturally fights against spherical symmetry. This creates a momentum paradox. It means our standard model of a gravity-driven collapse is missing a massive component. Gravity and rotation alone cannot make a sphere out of a spiral. To turn a flattened disk into a round ball, you need something else. You need a force that doesn't care about rotation. Rotation demands a disk. Reality gave us a sphere. Something overpowered the spin. To beat centrifugal force, you don't need magic. You need an engine. The only way to inflate a flattened spinning structure into a sphere is to inject a tremendous amount of energy into it from the inside out, effectively smoothing the wrinkles of the explosion. In audit terms, we call this an energy injection term. Think of it like a balloon being spun in a centrifuge. The spinning pulls it into an oval, but if you suddenly pump high-pressure air into it, the internal pressure pushes out in all directions, fighting the spin and forcing the balloon back into a round shape. The question is, what is the pump? The current investigation has two prime suspects, both of which are terrifying engines of physics. Suspect A, the cocoon breakout. When the neutron stars merge, they launch a relativistic jet, a beam of energy moving at 99.9% the speed of light. But this jet does not travel through empty space. It has to drill through a thick debris cloud known as the ejecta surrounding the merger. As the jet struggles to punch through, it dumps an enormous amount of heat into the debris, inflating a cocoon of hot gas. If this cocoon explodes outward, it could distribute energy isotropically, meaning evenly in all directions, creating that spherical shape. Suspect B, the magnetar wind. Alternatively, the merger might not create a black hole immediately. For a few frantic milliseconds, possibly lasting seconds, it might form a hypermassive neutron star with a magnetic field trillions of times stronger than the sun. This magnetar would spin wildly, whipping up a magnetic wind that blows matter outward in every direction, overriding the rotational flattening. This is where the connection to LF bots becomes chillingly plausible. Remember the blue flash. Remember the engine we suspected in Chapter 1. The mechanism required to make a kilonova spherical, a massive injection of internal energy, is exactly the kind of mechanism that would make an explosion look abnormally bright blue and fast. One possibility is that we are seeing different observational regimes of the same underlying engine. If you look straight down the barrel of the jet, you see a blinding LF body, exemplified by the cow. If you observe the event from the side, you see the spherical heavy element factory of a kilonova as seen in GW1 Saum 08-7. The glitch in the geometry wasn't a mistake. It was evidence of a physical override. The universe injected extra energy into the equation, erasing the memory of the spiral orbit. And whatever powered that override didn't just shape the explosion, it cooked the chemicals inside it. It left a signature that we still carry. Gold is not a gift, it is nuclear debris. For centuries, alchemists tried to transmute lead into gold, dreaming of a magical process that would perfect matter. But the universe doesn't use magic, it uses extreme physics. The process that creates the heavy elements in your jewelry and your smartphone is not an act of creation in the artistic sense. It is a catastrophic accident of nuclear physics known as the R process, or rapid neutron capture. When neutron stars collide, as confirmed in GW1 7000817, and as hypothesized in events like the Finch, they didn't just release light, they released neutrons, an unimaginable flood of them. In the milliseconds following the merger, the density of free neutrons spiked to billions of times higher than anything found in a standard star. These neutrons smashed into the nuclei of lighter elements like iron, forcing their way in faster than the atoms could decay. It was a chaotic, uncontrolled gorging. The atoms bloated, becoming heavy, unstable, radioactive monsters. But as the debris cloud expanded and cooled, the neutron flood stopped. The monsters began to decay, shedding particles to find stability. Most of this material ended up as radioactive waste, but some isotopes settled into stable configurations. They became platinum-195, they became uranium-238, and inevitably they became gold-197. To an auditor, gold is simply industrial slag, the stable chemical ash left over after the fire goes out. For a long time, this was just a theory. But But recently, the James Webb Space Telescope provided a crucial piece of evidence. While observing a likely kilonova associated with gamma-ray burst 230307A JWST detected the spectral signature of tellurium. Tellurium is a heavy element that sits right next to the R process chain that produces iodine and xenon. Finding tellurium is like finding smoke in a gun barrel. It confirms that the factory is operational. But this factory has a unique exhaust. The creation of these heavy elements, particularly the lanthanides, also known as rare earth elements, produces a curtain of high opacity. This metallic fog efficiently blocks blue light, which is why standard kilonovae turn deep red so quickly. It also explains why the blue flash observed in LF bots is so confusing. If some LF bots are indeed kilonova-related events, then an additional energy source, such as the engine we suspected may be punching a hole through this heavy metal curtain to let the blue light escape. The audit confirms the mechanism. The crime scene is littered with the byproducts of the event. But this debris didn't stay in the void. It traveled. Look at your hand. If you are wearing a wedding ring or holding a smartphone, you are holding the evidence. The gold in Earth's crust shouldn't be there. When our planet formed 4.5 billion years ago, it was a molten ball of rock. In that liquid state, heavy metals like gold and platinum would have sunk straight to the iron core, locked away forever under thousands of miles of rock. The surface should be barren of precious metals, yet we mine them. We find veins of gold in the crust. Why the leading hypothesis, Tier 4, is the late, heavy bombardment. Hundreds of millions of years after Earth's core sealed shut, our solar system passed through a cloud of debris, ancient shrapnel from neutron star mergers that happened eons prior. Meteors laden with this cosmic slag rained down on Earth, salting the crust with a fresh layer of heavy elements. This means we are literally mining the wreckage of the events we have been investigating. The anomalies of the past became the resources of the present. This connection changes the nature of the audit. We are not just observing the cow, the finch, or the sphere as distant curiosities. We are intimately connected to them. The lanthanides that color the kilonova red are the same elements inside the circuitry of the screen you are reading this on. The uranium that powers our nuclear reactors was forged in the same billion-degree cauldron that powered the spherical explosion. We are a technological civilization built on the waste products of cosmic glitches. Our investigation began with a flash that was too fast, known as LF bots. It moved to an explosion that was misplaced, the event called the finch, and it confronted a shape that seemed impossible, the near-perfect sphere. These paradoxes are not failures of the universe. They are failures of our models. They are glitches only because our simulation of reality is incomplete. The universe is telling us that engines matter more than we thought, that location is a bias of our vision, and that energy injection can reshape outcomes constrained by geometry. The blue flash wasn't a mistake, it was a signal. It told us that the death of a star is far more complex, violent, and creative than we ever dared to simulate. The audit remains open. The universe is not broken. Our models are just beginning to catch up.